Hello, and welcome to our overview of Fourier analysis. We'll be introducing certain points of both the Fourier series and the Fourier transform, as well as giving a real-life application to this mathematical process. So, why do we need Fourier analysis? Well, Fourier analysis allows us to convert any signal with no initial conditions to the frequency domain. In the Fourier series, this allows us to take any periodic signal and write it as the sum of sines and cosines by finding its particular Fourier series. There are several representations, such as sine and cosine, amplitude, phase, and exponential. There's also another form which can also change non-periodic signals into the frequency domain, which is called the Fourier transform. Fourier analysis allows us to see how much certain frequencies contribute to the signal. There are several limitations to the Fourier series, such as the Fourier series in particular can only be done on periodic signals with no initial conditions, and it must follow the derelict conditions. First of all, f of t must have a single value everywhere. There must be a finite number of discontinuities in a single period, a finite number of maxima and minima in that period, and the integral over one period of f of x must converge, which means it can't break off to infinity at any point. The limitations of the Fourier series specifically are the Gibbs phenomenon, which is basically discontinuities in a signal that leads to overshoots at positions when finding the Fourier series, which gives it the little Batman look when you look at the particular graph. This leads to inaccurate representation of the signal at these positions, but can be remedied with more terms in your series. The limitations of the Fourier transform is that it can only be done on non-periodic signals with no initial conditions. Here are the integral equations that represent both the Fourier series and the Fourier transform. The first one is in its sine and cosine representation, where we see an a0 coefficient and then both the an and bn coefficients, which are essential towards finding our approximation. And in the Fourier transform, we see the integral over all points of a certain function multiplied by a special e term. Now we'll be going into a Fourier series example with a problem from the book, which will be played in a YouTube video.
We'll do our Fourier series example. We decided to pull 5.9 from our signal subsistence book from the class. So in the example, it shows off this waveform, and it's 3 trapezoids, but of course it extends out. So if you'll note that it has even symmetry, which means it extends out, it's the same function on either side. So going into the function, we can see that we can describe it as 3 linear lines extended out from 2 to -1, -1 to 1, and then 1 to 2. So these are the actual functions that we'll be using. So the first coefficient we're going to talk about is the average value coefficient. It's going to be a of 0. So this particular integral involves taking 1 over the period from -2 to 2, and then of our functions. So we're going to have to separate them all out. And then after all the math, you'll end up with 15 over 2. So that's the average value of this signal in particular. Moving on, we'll have to describe all the other terms through cosine function. So we'll start off with a of n. It's going to look quite similar to the a0. However, it's going to be 2 over t0 over the same period of the function multiplied by our cosine function dt. So this would be the entire function drawn out, all the integrals separated and everything. So after all the math, taking the integrals of everything, you'll end up with 40 over square root of n pi times these cosine terms. And then finally, our last coefficient we'll have to solve for is b of n. And you'll note that it is 0 because of the even symmetry. So when you actually do all the math, it'll turn out that this side cancels out this side. Alrighty. So coming back, the main function will look like this. It will be typically a0, which is our first constant, plus a series with our A of n put in front of a cosine term. And then normally there would be a sine term, which would be your B of n. However, because that is 0, it all goes out to 0. So this would be our final Fourier series representation of the waveform.
Now we'll be getting into our biomedical example of a Fourier transform. And for this one, we decided to use this particular article using Fourier transform infrared spectroscopy to identify Salmonella enterica serotypes. I'm going to read a quick summary that a group has gathered from the article. Salmonella in food is a problem that can lead to illness and potentially death. There are varying degrees of pathogenicity between serotypes of Salmonella enterica, so it would be beneficial to be able to distinguish between them. Using FTIR spectroscopy, one can utilize the Fourier transform to represent the potential distinguishing characteristics between different serotypes. This transfer allows the team to generate an IR spectra that was used to identify the serotypes so that further research could potentially focus on deadlier strains of the bacteria.